Previous session we were talking about the concept of partition, a verb and a noun. Now, to partition as a verb, to partition a set, you can think of it as slicing up the Venn diagram of that set. So, like here's your set A, and here's a Venn diagram of that set, and you just cut it into pieces, and so you create subsets, and each subset is disjoint from every other subset. So each of them are disjoint relative to all the others. And that means that any element in the set, any point, if you're thinking Venn diagram, so any element in the point belongs to one and only one of those subsets. And all the subsets together, you put them together, you union them all, you get back to your original set. So that's the idea of partitioning. So just think of it as slicing up your Venn diagram. Right? And here in this case, just 3 subsets. Right? So we can do our first theorem now for this topic on equivalence relations. So if you have a set A and you have an equivalence relation, whatever it is, defined on the elements of that set, then the equivalence classes, remember what that is? An equivalence class is a subset, and every member of that class is equivalent to all the other members of the class. And you may have a second, third or fourth equivalence class, and every member of that equivalence class, they're all equivalent to each other, but none of those in the second equivalence class are equivalent to any of the members of your first equivalent class. They're disjoint. Okay, so we can show. So we'll prove it here that if you have any equivalence relation on that set, then that relation creates equivalence classes which partition the set. So you're slicing up your set A into equivalence classes, okay? And equivalence classes are disjoint. They have no elements in common, right? All right. So how to prove that? Well, so let me say what. Let me repeat what I just said, in a sense, in different words. You have a set, and it will be a union of disjoint residue classes of this form. So that's what we're trying to show, right? And with emphasis on the word disjoint. And the whole thing is the class, right? Well, here's your class, here's your set, any set with, let's say, n elements, okay? Now, that is just the same as this, so I'm just now taking the union of single element sets, right? That's the set of just one element A1, that's the set of element A2 and so on. So these just map, 1 to 1, okay? Now, from the previous theorem, 55, any element belongs to its own equivalence class. Right? That was a result that we proved in the previous session. Okay, so for any element, we can have an equivalence class. So we can now this class will contain usually more elements than just A1, but it does contain A1, right? So can you see from this you can derive this? Now remember, a set has no repeats. If any element is repeated in a set, just throw it out. So each element in a set is distinct. Right? We just define a set to be that way. We have no repeats. Right? Now, this set here will, on the whole, usually larger than this one. but at least this one includes A1 because of this. Right? Any element belongs to its residue class. You got this from the previous theorem. Okay, so this will be equal to this, right? And if we get repeat elements, just throw them out. Throw out the repeats, so that you only have one copy, if you like, of each element. All right. So next step is to try to show that these residue classes are disjoint. So in other words, they're either identical or disjoint. So that's what's being said here. Okay. Right. So let's see if let's see the consequences. If we have, say, two of these residue classes, I know the ith one and the jth one, and let's say they do have some, at least one element in common, right? So let's say there's an element here that belongs to two of these residue classes. So the intersection, the set intersection, this symbol here, like this. So that there's at least one element in common in two of these residue classes. Okay? So you've got something like this. In other words, the intersection of two residue classes is not zero. Right? It's not zero. It's not the empty set. Well, the empty set. It's not the empty set. So if that's the case, if there is an element in common, what are the consequences? What does that imply? And I'll show you. It means that A bar and B bar, in other words, these two residue classes, they're the same. So A bar is B bar. Right? That will be the consequence if this is true. So we can prove that, and that means that either two residue classes are either disjoint, they have no elements in common, or they're the same. They're just the same residue class. Okay, so that's what we'll. So given this, given this, that there is an element that belongs to both, we will now try to show that these two are in fact the same. Right? So let's try to do that. Now look, if X belongs to the intersection of two sets, remember a residue class is it's a subset, which is a set. Okay. So if X belongs to the intersection of these two, it belongs to this one and this one. Right? So X belongs to A bar, the residue class of A, and it also belongs to B bar, so it's a residue class of B. Right? Now if X belongs to A bar, then by definition, what does A bar mean? It's all those x's that have this property, that X is has an equivalence relation with A, and if this is true, then that's true. X has an equivalence relation with B. All right. Now look, so if X is equivalent to A, then it's an equivalence relation, right? So the three properties hold: symmetric, reflexive, well the other way, reflexive, symmetric, and transitive, right? So if X is equivalent to A, well then A is equivalent to X. That's the symmetric property, okay? So A is equivalent to X, and X is equivalent to B. Therefore, A is equivalent to B. That's from the third property, the transitive property of an equivalence relation. Okay, so A is equivalent to X, and X is equivalent to B. Therefore, A is equivalent to B. You've got this. All right. Now, from the second part of Theorem 55, that was from the first part. So what we did in the previous session. So from the second part of Theorem 55, if A is equivalent to B, then A bar equals B bar. So the equivalence class of A is equal to the equivalence class of B, right? So if there's a common member, these two equivalence classes are the same. Okay? That's from part 2 of Theorem 55. Okay? So equivalence classes are identical or disjoint. Okay? Identical or disjoint. So go back to here. Here's your A. It's a union of identity. What's the word? Equivalence classes. Okay. Now they're either identical or disjoint. So if you have two that are identical, throw out the repeat set. Throw out the repeat class. Okay. Because your set that has no repeats. All elements are distinct. Okay. So if you throw out the repeats, you're just left with a union of residue classes, all these bars, right? And none of them are the same because we've thrown out the identicals. So that just leaves disjoint residue classes. These now are only disjoint once you've thrown out the identical residue classes. Okay, so A is then of this form. These are all disjoint, and when you union them all the disjoint ones, you get A. Well, that's the definition of a